voting stuff, like polls that people do, and they say something like, we think 42% of people are going to vote for candidate A. What you always see at the bottom of the screen then, or the bottom of the article, whatever it is plus or minus 4%. So for example, you see like candidate A, good old candidate A, right? 44% will vote for them. Candidate B, let's say 48% will vote for them. Why doesn't that add to be 100%?
People don't vote.
Some people are unsure. They're undecided. And at the bottom of the screen, you'll see plus or minus 4%. So to be honest, this could actually be the reverse, right? So does this mean candidate B is going to win? No, for a lot of different reasons, but the most basic one is these numbers are estimates. They could be off by this much, right? All right, maybe. Have you guys ever seen that thing before? I mean, hopefully.
Yeah.
If you pay attention to anything, you're going to see that kind of thing. Okay. So that's part of what we're going to discuss is how to figure out that number, that plus or minus 4%. Where does it come from? Do they just make it up to cover their ass? They're like, let's make it plus or minus 8 because we're really not sure. But no. It's a math formula that actually gives it to them. So to get into this idea, I want to do some stuff that we're used to already. We could do all this stuff before anything we learned today. Let's say I have a normal distribution. And let's say the mean is 50. And the standard deviation is 2.9. Let's give this some idea. 50 minutes. Let's say this is the amount of time that the dryer takes to dry the clothes. Is that cool? Just to give it some kind of physical meaning. So a certain dryer, give or take, spread it this much. So between what two numbers would there be the middle 95%? Between what two times? The middle 95%. This is a problem you can completely do right now, so do it. Don't say anything. You can talk to each other, to be honest. Try to figure this out. This is a problem I could have put on this test. It's actually a problem I did put on this test, to be honest. The temperatures. You could be more precise now. It's not a z-score of 2.
What is that? What does that say right there?
Between, I'm sorry. Yeah.
2.5.
Huh?
2.5.
Nope. So just like on the test with that temperature bounding the middle, whatever percent, your first step is going to be to figure out what? Well, your first step is going to be to draw the damn picture, right? Mm-hmm. So you have a visual. So the middle 95% chunk. Keep going. This ain't a quiz or anything. It's just a little example. Talk to each other. You can get it completely wrong right now. We'll figure it out. Try something. Yeah. Almost. So of course, if there's 95% inside, there's 5% outside, there's 2.5%, 0.025 over there, right? So when you look that up, what z-score do you get? Almost.
Oh shit. I mean, shoot.
There you go. 1.96, right?
Yeah.
Yeah.
I like it.
Forgot
I
I
like
cut
it.
him in half.
So what's this one?
1.96.
Positive 1.96. Is that cool?
10
So for a normal distribution, they'll always be plus or minus same number. The middle whatever percent. Okay. Just like it was, we've done this problem a few times now.
50 plus 1.9.
And now what formula are you going to use? Because I want to know times. These aren't times. This isn't t minus anything. We're not shooting this dryer off into space.
You don't know X.
Yeah, I got to figure out x. I got z. I got mu. I got sigma. Can you get x's now? Yes, sir.
So 95% of the data is, or it's 2 standard deviations plus and minus is close to 90.
Yeah. The empirical rule is sort of they rounded it to make it quick to say. It's not exactly. There's your exactly, yeah. We can be much more precise now because we have that, what I call empirical rule on crack, the z-score chart.
Yeah, is this what you got?
So what formula do you use to convert these back into x scores?
X equals mu
Yeah.
X-score.
plus
The x score formula, yeah.
Z times standard.
So just like you can calculate z-scores, which hopefully I think everybody is pretty comfortable with calculating z-scores, which is really good. You need to become just as comfortable, it's the same thing going backwards. If I know the z-score, I can use it to figure out what the x-score must have been. So then you do that for each one of these. Actually, let me see if I can get away with this. Is this cool to see this? Is that all right? 50, give or take this much. So it's not a bad idea to figure out this part first. And then you just added the 50 and subtracted away from 50. Yeah, what do you get for this part? Anybody do that part by itself?
5.684.
So you get
55.684.
44 points
316.
up to
55.684.
55.684. So that interval, how confident are we that any data point from here shows up in that interval? We're 95% confident that this interval catches any specific data point. Is that okay to say?
Yeah.
Everybody understand what that means? Of course it is, because it catches how much of the data?
95.
Catches 95% of the data. So how sure are we that it catches any specific data point somebody wants me to find? We're 95% sure. There's only a 5% chance it doesn't have that value. All right, let me stop there for a second. Okay, cool. Now, this is still not up to where we are now in sophistication, to be honest. This is still not as sophisticated. What do we normally work with in statistics?
Samples.
Samples. So, let's do this problem again.
Oh, lordy.
Same stuff. But now, if we take you write the whole word out. Between what two average times would 95% of the average times be? Change what you find. Sorry.
Any formulas?
What's the only thing that changes from what we just did here?
Standard deviation.
Yeah, the standard deviation has to change. Why has it got to change? Because I took a sample and I asked a question about the sample means. Those two things happen, I got to change the standard deviation. This one I use because it tells me how spread out individual times are. Now I've got to use the one that tells me how spread out groups are. So what would this sort of become here? This would sort of become this. What change? How does the standard deviation change? So it'd be mu plus or minus z times the new standard deviation. Is everybody cool with that? Mm-hmm. If everybody was cool with this, which hopefully everybody is, this isn't that big. This is exactly where we are coming into today, and this is still where we are, to be honest. But I know now I got to change the standard deviation when I take samples and ask about means. I've got to change that. This is not that big of a step. Yes, sir.
Do we use the same exact as this square?
Yeah, exactly. It's still what z-scores contain in the middle 95%. Still plus or minus 1.96 times 2.9 divided by square root of 11. So what's this piece going to be? Let's see. You guys probably. All right, out there if you want to. It's not easy to do division by square root of 11 in your head.
What do you sell for?
I would try though. What do you get? 0.874?
Mm-hmm.
Yeah. You get what?
No.
I get 1.714.
Oh, that you multiplied it by that. We haven't done that yet.
Okay. Does everybody understand what's happening? Is everybody decent right now? You guys, this is nothing new, to be honest, at all.
No.
Nothing new at all. And again, this is related to the idea that if I went out and looked and got individuals, I would expect 95% of them to be between certain heights. I mean, can I just say that without getting too specific? If I went out, I would expect 5% of the people I could find, individuals randomly find, would be like taller than 7 feet or shorter than 4 feet. I mean, I expect 95% of them to be within this. If I took groups, random groups of size 11, now it's going to be even harder for their averages to be that far away. They should be contained in a smaller interval.
Yeah.
This is the idea, that if I take a group, now the interval that catches 95% is going to get smaller. Why? Because now groups are all going to get closer to the middle. Because the standard deviation, of course, gets smaller. So here you get 48.286 up to 51.714. Is that cool? You guys got that?
Mm-hmm.
So between those two times, I would find 95% of all groups of size 11, their mean would go in between there.
Is there a difference between the brackets and the parentheses or no?
Where did I use brackets? I'm
I
sorry.
was asking, can you put, because I was reading and like it would show brackets. I don't know if there was a difference.
Did they show? All right. So in algebra, this versus this. I always say this looks like half of an open circle. So that's for don't include. Remember, open circles, you don't include it. And this looks like the letter I for include, so that would be you include it. Right? So in general, when we construct these intervals, we don't include the endpoints. So we put parentheses on the endpoints. I'm not sure. You'll have to show me. It might have been something different they were doing. All right.
This was free.
Now, and again, I don't know, some of you guys might be underwhelmed so far with today. You're like, we haven't learned shit, Jeff. Thanks. This is all shit we've done before. It's good to review. So here's what's going to change today. This is huge. This is our first step. We've done everything we've done so far has been getting ready for what we're getting into now, to be honest. Because what do we normally, this is kind of insane. We normally don't know this. right? That's the whole point. We normally, now, surprisingly, we do sometimes have that. And let me give an example of why that makes sense. And then later today, we're going to talk about, well, what the hell do we do when we don't know this either? Shit. All right, so we'll get there. So everybody got this here? Okay. All right, so here's the formula we were just now using. Is that cool? That's basically the formula. Sorry, just give me there we go. That's the formula just now using. So if I don't know mu, and I take a sample, what's my best guess for mu? If I take a sample, I can figure out what? From this
Z-score.
X. Come on now. What is mu?
The mean.
The mean of the. So when I take a sample, what's my best guess for mu?
Oh.
The mean of
the
that.
mean.
Sample mean, X bar. So in reality, we normally have X bar. So what's going to happen now, what's interesting is, what we're doing is we're figuring out, this is our first step into, okay, when you take a sample, you get specific information from the sample. How do you then infer something about the whole population? So it kind of makes sense that you would expect us to go, all right, if 28% of my sample does something, my best guess for the population is 28%, but it should be give or take, just to cover my ass a bit. But the give or take comes out in the work. It comes out in the math. It's kind of nice. So here's the idea. The mean exists somewhere. The mean is just sitting there somewhere. I'm going to make this interval. And this interval is called a confidence interval. That's why I said that earlier the way I did. It's a confidence interval. Okay. I'm going to construct it. So my X bar, is it going to be equal to the mean? More than likely it won't, right? Any sample I take, I would put money on its mean being different from the actual population mean. I would expect it to be close, but I almost always expect it to be different somehow. It'd be really weird if it was exactly the same. I mean exactly the same. That would be kind of weird. Is everybody with me on that? We talked about that kind of thing on day 1. Okay. So so the mean is sitting there somewhere. The actual mean time for dryers to dry, the actual mean lifespan of dolphins, whatever the shit it is, right? It's sitting there, and I can't get it because I'm probably not going to be able to look at the whole population, right? I'm not going to be able to go check everybody's freaking dryer out in the United States, right? I'm just not going to do that. It'd be a really weird show. I don't think many people would watch it. I'm going to take a sample and figure out a sample mean. So let's say it's close. Here's my sample mean. Now, if I make a confidence interval go down so much and go up so much, so for example, if I make a 95% confidence interval, that means 95% of the time that interval will include the real mean. So if everybody in here made a confidence interval, got your own sample mean, made your own confidence interval, 95% of those confidence intervals would contain the real mean. 5% of them would be like, somebody takes a sample and their mean just randomly is really low. And when they make the confidence interval, does it include the mean? No. So 5% of the time, that would happen. If you use the z-score, the 1.96, because that's the one for 95%, right? If I use one for 90%, then 10% of the time, it's not going to catch the mean. Use 99%, then 1% of the time, it won't catch the mean. All right, let me let all that sink in. Yes, sir?
What if the sample mean is a little above the actual mean?
Like this first situation.
Yes, and then and the mean is a little below. That means the actual, like the data, or the at least you're out in some percentage more than the 5%, right?
So the whole idea is you construct this interval first, like we did like this interval, right?
Yeah.
You construct the interval first, and then you can step back and say, in that case, there's a 5% chance my interval was too high or too low. It didn't include the real mean. So here I would say I am 95% confident that this interval from 48 something minutes to 51 something minutes contains the real mean time it takes for dryers to dry. That's what I would say here. I'm 95% sure. Why? Why am I 95% sure? Because only 5% of the time it's going to be too far off. Yes, ma'am?
In one situation, these two will be equal.
Yeah, sometimes, sure. It's possible. It's very unlikely, but it's possible x bar equals mu. And that's great. What's wrong with that? It's still in the interval then, isn't it? Yeah. Okay. All right. So let's get away from theory. Let's get into a concrete problem. Let's do that. I'm sure some of you guys will like. It sounds a little better, Jeff. Okay. Let's do a concrete problem. So here's for a confidence interval for mu sigma known. So that is the confidence interval formula. So on a test, if I say make the confidence interval, make a 95% confidence interval, you know you're going to use one of the formulas that's got the plus or minus in it. That's the whole idea. There are going to be 3 of these formulas we're going to use, each of them for different situations.
Instead of doing sigma over square root of n, can we just put sigma x
Sub
bar?
x bar, sure.
Okay.
Sure. If it's clear to you,
Okay.
you could just put sigma sub x bar here. I like it. All right, so here's the situation. Let's say we take a sample of 42 gas stations. We find a mean gas price of, I don't know, what's gas cost right now?
308.
350?
What the hell? Where are you getting gas?
Not in Carmel Valley. I'll tell you that.
308.
Rancho Bernardo, you stay away from that shit. All right, let's say we find a mean gas price of 361. Is that right?
Schmooly.
Is that too much?
Not as bad as $5.
My gas is 308.
I don't know. It changes so much.
Yeah, my gas is 308.
I don't even look anymore. I'm like, I need gas. I might as well not know. Shit. Just give it to me. I just go to Arca.
There's one place that's 327 and I won't go there.
All right. You know Google Maps shows you prices
So does Waze, yeah.
since a long time.
Always.
Yeah. You got that Gas Buddy app too. All right.
So let's see.
So what is this? What symbol would I use for this?
Mu.
X bar.
X bar. Why X bar for sure? Because where'd it come from?
A
A
sample.
sample.
From a freaking sample, right? So you guys have got to slow your roll down when you read through these problems, especially with standard deviations when we get there. Right now we're assuming we know sigma, so they have to be very explicit. We find this is X bar. And sigma is known to be, let's say, what makes sense here, John? 31 cents. Now, my first question is, why am I allowed to do anything like this for this problem? What is it about this problem that allows me to do what I need to do up here? That's why I have to do this, but what allows me to do this?
Because n is greater than 30.
Yeah, what's n?
42.
Which is bigger than
30.
So the means would be
Normally distributed.
normal enough. Are you with me?
No.
What step do I need that for? Well, if I say construct a 98% confidence interval, what's the only way I can convert this back to a z-score? I got to use a z-score chart, and it only works when I have a normal distribution. So why could I do the other one where I only took 11? The first one we did, I said we only took 11.
It said it was already normal.
It was already normal to begin with. It doesn't matter how many I take then. It's already normal. Right? This, do I know it's normal?
Yeah.
No, not at first.
Well, no.
But since I took a sample big enough, I know those means will be normal enough. Okay, let me stop there. Everything comes back. Okay, so this is an example of a problem that really isn't new, to be honest. It's just putting stuff together in a way we haven't done. But this is full of old stuff. Now, of course, when I say old here for us, it's not really that old, but. So what do I know? I know X bar is 3.61. What else do I know?
42 gas stations.
Good. I know N is 42. I know sigma is
0.31.
0.31. Oops.
Then you gotta find Z.
And now you got to just, now, do I have everything I need here? The 98% confidence interval. Don't say anything out loud yet. Can you figure out, what do I need to get from this? What do I get from this? Z-score. I've got this, I've got this, I've got this, I don't got this. I get it from here. So don't say anything out loud. Take a minute. See if you can figure out what this, can you figure out what this is? So what's it going to look like? It's going to look like that. So now I can do the same thing we did earlier. Figure out those Z-scores.
Yeah.
What's over here? 0.01.
Is it negative 0.01 or?
No, areas can't be negative. But the Z-score is going to be negative, you look up. Negative 2.33. I like it. So this is going to be
Positive.
And look at the formula. Look at the formula. Why doesn't it really matter about negative and positive? Because it's built in. That's why it's got a plus and minus, because it knows it's going to go both up and down. It's built in. All you care about is a 2.33. So now you just plug and chug. Right? You got everything you need. So go ahead and try to finish this out. Throw stuff in there. Try to figure it out.
0.01. No, 3.99 is closer.
Yeah, I should do that.
That makes sense. Calculator is.
Hmm.
0.111. Why 4 places?
Because I like to be accurate.
Well,
Like 499.
Pretty sure it's not right. Which I usually am.
Are you sure?
Yeah.
0.61 plus 0.111. 3.721. Correct. Would it be 2.499 or 2.5?
That's interesting. Huh?
Would it be
What do you guys get for the error piece here?
0.111?
0.1115.
0.111.
If it's 5, it would be 0.112.
0.1115.
So it's 112? 112?
Yes.
No? All right. Hey, Jeff did not pick up a copy. Jeff has
No, it's
crowdsourced this.
0.1114.
I love you guys so much.
Yeah, I was right. 0.111. 0.1.
Yeah, 1114. All right.
Unless we're on with the 400.
So in general, it's a good idea to take this one more decimal place than this. That's a general idea. All right, I like it. All right. Is everybody cool with that? I love how people just go insane with it. All right. And now you just add and subtract that. What do you get here?
3.499. 3.721. Would you round that to 5 or no?
Say again? Normally, if you want to, you can round these to the same as this. So 3.50 to 3.72. And plus, this is money. We could argue gas stations listed out to the third place, but this is money, so we can make it to money. Now, you're already like over enthusiastic about this problem in the first place. You're gonna go crazy with this last piece. You always have to write a conclusion explaining what the hell you just got. Right? Don't just say, I got 3.5. No. We are farmers. No, we are how certain about something? We are 98% confident. We are 98% confident that this interval, my God, this is real life shit, so you better put units on this sucker. So the interval, $3.50 to $3.72. What about that? We're 98% confident that the interval does what?
Contains a mean.
Contains a true, I use the word true, and that means population. Contains the true mean
for the same
gas price. So that's the kind of statement you will have to write every time you construct confidence interval. Yay, Jeff, you made it even better. Yeah, laugh it up, math boy. All right.
Jeez.
So, confidence intervals are misunderstood, and you're like, we just learned about them, so we don't understand them at all. This doesn't mean that it can't be outside. Of course, what's the chances that it's outside of this? 2% chance. All right. So if 100 people made their own sample, made their own confidence intervals, 98% confidence intervals, I expect 2 of them, on average, to not actually contain the real average. Right? Now, in real life, we don't know the real average. Do you understand? So there's no way to really know. Okay, I like it. Okay. Let me do one more thing with this, and then we'll take a break. Now, I don't know if you guys picked up on this, but I called this piece a certain name just a second ago. I gave this a name. Not Fred or something. What did I just call that? I don't know if anybody picked up on that.
Error.
Error. That's how much I think it's off by. This is my best guess. It's what I see in the sample. It's always my best guess. And this is give or take this. That's my error. It's how far off I think I am. To a certain degree of confidence, right? So this piece is called the error. Error. So, let me write the error formula by itself. G equals Z sigma over square root of n. That's amazing. Because that's what the error is. Is that cool so far? In fact, I think in the book you'll see stuff like x bar plus or minus e, which I sort of hate a bit. Why not just write the formula out? But oh well. Do you see what there's? That's e, so that is this. All right, that's amazing. I like it. How are we doing so far? Is that? And again, does it make sense to call it that? Give or take. Give or take, so that's how far off I think I am. Or how far I want to be, or whatever. So in real life, we sometimes want to be able to get within a certain amount. We want to make the error only this much. So if I'm like estimating how many people are going to come to this party, and my error is 300, Oh, okay. Shit. Let's cut that down a bit. So I want to know how large of a sample do I have to take in order for the error to get small. Now watch. As the sample size gets bigger and bigger, what happens to E? Smaller and smaller. And why does that make sense? The bigger the sample, am I more or less sure about X bar? More. The bigger my sample is, the more certain I am about everything I see in the sample, right? So you can see that. The bigger I make my sample, the smaller error becomes. Holy shit. That's day one shit put up in a math form. I like it. Cool. So, I want to solve for n. How do I solve this for n? Don't say anything out loud. Take a minute and try to do it, all you people that came from algebra. Let's see if you really, really pass that. Solve this sucker for n. N, yes. Solve it for n. Yes. No. It's just by itself.
Not first
Yeah.
thing.
It's not based on that problem over there at all. Now, most of you are doing it in your head, I guess. I don't know.
Oh, you just did it the opposite way.
You're supposed to have two apples in the square root, right?
Yeah. He did. Yeah.
Say again?
He left his with square root.
You left it with square root?
We
No,
did.
no minuses.
I got n equals
Z E
two
sigma squared.
No, I mean z sigma
All right.
E
So a
squared.
really good first idea would be to multiply by the square root of it.
So, aren't you trying to figure out? Oh, you
Doesn't matter. You
Yeah.
could square first or do this first. Doesn't matter. Right? The variable I want to solve for is on the bottom. So the first thing I do is I get it out of the bottom. That's the worst place for it to be. Bam, bam. So now I get square root of n times e equals z sigma. Now I divide by e. And then I square both sides. So I get n equals z sigma over e squared. Why does this make sense? The smaller I want e to be, the bigger this becomes, which again goes along with what we were saying. So if I put 0.111 in here, and I put 2.33 here, and I put where'd it go? 0.31 here. What would I get? 42, because that's a sample of 42 for this problem. Gives me an error of this. So the biggest mistake people make is, I'll say something like, well, how large of a sample in order to be within 5 cents? 0.05. And people just put 0.111 in there because they just say E is that. No. To be within 5 cents or $0.05, right? What's E going to be then? .05. Within is the key word. I want to be within 5 cents. How close am I right here? I'm within about 11 cents. Now I'm saying how big of a sample do I have to take to be within 5 cents? 0.05. So now I let E be 0.05. So I put N equals 2.33 times 0.31 divided by 0.05 and square all that stuff. It's definitely going to be bigger than 42. The question is how much bigger? I'm going to say like 100. Right, Jeff? 170 maybe?
200.
200?
208.69.
208 point
69.
something?
Yeah.
1.686.
And it doesn't matter with point whatever, you always round up.
209.
Because you need at least 208 point something. So if you round down, you don't have enough. You're not going to be within 5 cents. So a sample of 42 makes the error 11 cents. If I want to make the error 5 cents, I need a sample of 209.
Is that 2.99?
2.33.
Well, it's 2.20 something.
33.
Where'd I get this from? Yeah. So 209. Okay. Let's take a break. Come back at, let's say 35. 10:35.